data is then processed, and the area of the region of interest is isolated. And then, in this case, we made an SLA model to begin with of the surgical stencil. And later on, there was a whole aperture cut which followed the Langer lines. Regrettably, the patient decided not to go ahead with it at the end of the day. But what I can say is when we fitted this onto his face, it almost fitted like a vacuum onto his. So, you know, it was quite hard to remove. It fits so perfectly. Makes the Phantom of the Opera look like a poor fit. Another example this is from H.R. Johnson, still in business up in just north of Stoke-on-Trent. And they wanted a way of making tiles. And the conventional way of making tiles is to have, usually girls, handcraft plaster images, which are then copy milled to make hard tooling. It can be quite a lengthy process. And so what we did, went outside this over at Warwick, and we actually pinched some leaves off the road in the gutter, took it onto a blank tile, spray painted them white. Then we used a laser scanner from Highmark. Is that correct? They're no longer in business. Nothing to do with myself or Chris, apparently. So, that's a laser strip scanning system. And then generated this triangulated data, and using ArcCam Pro, filled in all the areas where you couldn't quite get in because there was shadow, and also made sure there was no undercut, and also flattened the profile a little bit because it was actually stood up too much. And this is the result. And as you can see, it's quite a faithful reproduction of the actual leaf. Strangely, you can actually see the veins in the leaf. And then the guys that made the tile put this massive, greatly thick dollop of enamel on the top to cover it, so glaze on the top to cover it. So they missed a lot of the data out after all that. This is a recent project, 2,000-year-old Roman bottle from in excavations from Leicester. Quite hard to scan because it's actually partly transparent, partly opaque, metallized surface, flaky, so it falls off. We tried a few different techniques, including our laser scanner, and we couldn't capture it. All we could do is capture the opaque bits. We can't spray paint it white, but we can't remove the paint afterwards, and we couldn't put anything on it because we couldn't be certain we wouldn't remove this patina. So we actually enclosed it in a latex glove, took it on our cyclone, put a bit of silicone oil on, and we actually scanned it, captured the data. Our friends at Materialise used 3Matic to register it, and then we made an SLA model. Fit is not perfect, primarily because the latex glove couldn't be stretched as tight as we'd like. But the bottom line is we worked the process through. The guys in the museum got their bottle back with still having the glaze intact. There's probably other ways of doing it, and I'd be interested to see if anyone's got a suggestion. CT, because CT it. We're going to do that in a minute. What about anyone? Structured light, possible or not?
I thought so, yes. It's tricky because of the reflectiveness of the surface, but it should be possible.
We thought of all sorts of. We actually filled the bottle up at one stage with an opaque liquid.
That would do it.
On our scan it wouldn't work because you get some parallax errors through the glass. The glass is quite thick in places. But now, if anyone's got a better suggestion, the latex glove only comes in a couple of sizes and only seems to fit the particular bottle shape. So the next one might not be so easy. This is a project we did with Royal Worcester where they wanted to archive product data from an existing range of products where there's no CAD. And this project shows that you don't have to collect thousands of points. In this case, we actually carefully thought about where to capture the information. We actually marked lines on the object. And with a very cheap microscribe articulated arm, £2,000 or £3,000, just carefully collected a series of points. And then loading into Delcam power shape, and a series of effectively wireframe, which then can be generated, rotated round to generate the object. And from that we made actually a simple Z-Corp model. I was amazed, because having had the problems in the past of processing data, this was actually dead easy. I mean, it took us longer to choose where to to mark up the object. So an hour's worth of scanning, an hour before that to prepare, and then to actually generate the CAD model, 30 minutes. But we didn't have many points. So this is a nice way of doing it. It only worked because we wanted it to make it circular. The original object was not perfectly circular because it was handcrafted. If you decide you want something that's perfectly circular, don't capture lots of points because that will just confuse the hell out of the software. Volumetric scanning. Richard's already mentioned CT. There are other techniques that don't just capture the surface of the object, but capture also the internal information. So if you've got a very complex casting, you want to have the internal features. This is one way of doing it. It collects the information in the form of voxels. So rather than having a surface, you actually end up with a thickness to it. If that makes sense. You end up with an element. There are two primary methods that I can think of. One is medical scanning, so that's CT, MRI, and ultrasound. And the second is a destructive scanning technique. CT scanning was developed for medical scanning. And you'll see later on today the case studies, many of the medical cases use CT scan data. All that CT is really is a series of X-rays that are combined mathematically to generate a slice of the human body. And it's the actual mathematical processing that gave Mr. Hounsfield his Nobel Prize, because that's the clever bit. Once you amalgamate all those slices together, you can then have a 3D object. And the interesting thing is that the material you pass through affects the image at the end. So when you have very low attenuation materials like air, you actually have a dark colour. And when you get into things like tooth enamel and fillings, it actually interferes with the process of the X-rays through the human body and leaves a white area on the scan. And that's a series of scans from a CT scanner. Once you have your CT image, you can then do some contrast enhancement with it, so you can decide on what you want. This is the area here. This is a fractured acetabulum. So this person probably had a fall from great height or been involved in a car crash. We can then isolate those areas of interest, and we can then grow those separate. So we can also separate those out. So you've got this area here, which is the same threshold level, and now we want to isolate the acetabular area from the pelvic head, and so effectively we can sorry about that, to regular updates from ABG through my Paris software. So now we have two components. We also have to do some interpolation, particularly on the older scanners. The scan thickness is quite thick, and it's quite coarse data. So you then have this sort of image, and using things like materialized mimics, we can actually smooth that image down. This is getting less of an issue. The latest scanners are working on 0.6 of a millimetre resolution, which is not as good as we'd expect in engineering applications. It's significantly better than the 2 millimetres we were used to. We also have to interpolate between slices, and so you end up with that's the bone you want. This is actually the CT image, and then there'll be some smoothing that takes place in the software to reduce these steps. That's this area of the hip without the smoothing. When you put the smoothing on, it actually improves it dramatically. These are actually very poor models, aren't they? These are old models from Materialise, but you'll see some models in the Innovation Centre at lunchtime which really show the capability of medical scanning and medical prototyping. And lastly, we can actually generate these wonderful colour images which have revolutionised the way that medicine's taught and the diagnosis process. Here's some models. That's a model of a patient with an area of the maxilla and mandible missing.